Hello, everyone. Welcome to the 2021 ACOM Seminar Series. Thanks for joining us today. It's an honor and a pleasure for me to introduce Dr. Joel Thornton today. He's professor at the Department of Atmospheric Sciences at the University of Washington in Seattle. Joel got his bachelor's in chemistry at Dartmouth College, his PhD at the Department of Chemistry at the University of California, Berkeley. He did his postdoc at the Department of Chemistry of the University of Toronto, Canada. And many of you might know him because he's been participating to several field campaigns like FireX, Weekend, the Utah Winter Fine Particulate Study, just to mention a few recent ones. And I personally know Joel from his time in Finland in 2012 and 2013, in which he contributed to identify that the Finnish boreal forest was a large source of low volatility secondary organic aerosol. And today in his talk, he will tell us about our current understanding of isoprene and monoterpene chemistry in different environments. Before we start, I'd like to remind you that you can type in your questions anytime. Just scroll down on the webpage you're looking at now and type in your question, and the question will be read by me at the end of the talk. And with that, I introduce you to Dr. Joel Thornton. Joel, take it away.
Okay, thanks very much, Ali, for that introduction and for the invitation. Really happy to be able to present some work we've been doing in my group on the chemistry of biogenic VOC. And I just want to, before we get too far, make sure that my voice is coming through. So if not, I guess you can try to let Ali know or something and he can chat to me. And then also thank the sponsors for a lot of this work, the Department of Energy, National Science Foundation, especially the Environmental Chemical Systems, and also the Atmospheric Chemistry Program. And then we will be showing some work from the Cenex campaign, which was funded by NOAA. So I was originally putting together a talk about the work on the recent fire-related field campaigns that we've been interacting quite a bit with NCAR folks on, including WeCan and FireX-AQ, as well as the chamber study called Moonlight. And we've had quite a few interesting results that I would like to point out. And just my guess, though, was that this person right here, Brett Palm, who I guess doesn't look so much like this anymore, a younger view of him, is now at NCAR and has probably explained a lot of this or would do a better job explaining it than myself. But that was work done by Brett himself, as well as Xiaoyun Peng and Carly Fredrickson, two graduate students in my group. So I won't be talking about fires today. I figured I would talk about something a little bit different, a collection of things that we've been working on from here and there in my group and with collaborators elsewhere. So I probably don't need to get too much into why we should study biogenic VOC chemistry with this group. That is to say that their centrality in issues related to air quality and climate through the formation of ozone and the limitation thereof through interactions of VOC with oxidants and nitrogen oxides, as well as their contribution to particulate matter mass through the formation of secondary organic aerosol, as well as the contribution to new particle formation and growth, which then leads to possible feedbacks between the biosphere and through the climate system with aerosol cloud interactions. But that is something I think just mainly motivates why we need to understand the chemistry of these species in detail. And what I'm going to try to convince you of is that through their interactions with NOx, as well as interactions of the oxidation process in different environments, is still shrouded in some fair bit of mystery in terms of understanding that system quantitatively, the system of biogenic VOCs reacting in different environments. And so I'll just try to be pointing that out as we go along in about 3 or 4 different snippets of the science that we've been working on in this case. And when we talk about biogenic VOC, in their oxidation in the atmosphere, this is probably the view that we had about 10 years ago or so, where an oxidant initiator in the form of the hydroxyl radical or ozone or nitrate radical, chlorine atoms, would lead to the creation of a peroxy radical. And the peroxy radical really, in terms of the impacts of biogenic VOC, either on ozone formation or particulate matter formation or mass growth really is going to go through this peroxy radical, and its fate will ultimately determine the impact of VOC generally, but also biogenic VOC in particular. As you see here, this peroxy radical undergoes a number of possible fates. It can react with nitric oxide. That process is where we have ozone formation when nitrogen dioxide is produced in an alkoxy radical. But that can also be limited by the potential for these peroxy radicals to form temporary or permanent reservoirs of nitrogen oxide radicals in the form of organic nitrates. And here I'm specifically calling out alkyl nitrates, although there's also peroxy nitrates that we should be worried about. And then when the NOx concentrations are low, this peroxy radical tends to have other fates, which would be reaction with the hydroperoxy radical, HO2, to form, again, a reservoir of hydrogen oxide radicals, or a sink of HOX in the form of organohydroperoxides. And in the case of particle formation, we generally have thought that this pathway here is typically more favorable to forming condensable vapors, because you tend to maintain the carbon background. You have less fragmentation through the process of alkoxy radical decomposition that you would have enhanced by the presence of NO. And so you can think of this general picture of peroxy radical fate in terms of ozone formation and particle matter formation by thinking about which pathway they might be going down. And again, through 3 or 4 sort of small stories, if you will, I'm going to highlight that there's still quite a bit of uncertainty, even though we have been spending a decade trying to unravel this process. We are making progress, and we're learning actually that this is not the complete picture, and I'll be pointing that out, but that still we are fuzzy in some really important parts. So I'm going to jump right in. And most of those interactions, or sorry, most of those stories I'm going to talk about involve the interaction of peroxy radicals with NOx and or the competition of other pathways with the reactions of peroxy radicals with NOx. And in the case of isoprene, reacting with an oxidant, you get a suite of peroxy radicals forming. And through work involving Calvin Bates, Becky Schwantes, and so on, really updating our understanding of the importance of this chemistry and the removal of NOx throughout the global atmosphere. It turns out that over just the southeastern United States, this one molecule, isoprene, is removing about 10% of the NOx, and perhaps 50% of the NOx removal is occurring through this formation of organic nitrates over the Amazon and other equatorial tropical regions where there are large sources of isoprene. But ultimately, the alkyl nitrate fate in the atmosphere is crucial for understanding this impact of interactions between isoprene peroxy radicals and NOx. And so we would like to have a detailed understanding of which nitrates are formed, which nitrates last, which are being essentially converted back to NOx through various recycling pathways, or moved to even more permanent sinks of NOx, such as nitric acid, through the process of aqueous phase hydrolysis of tertiary nitrates and so on. And we have not, 10 years ago, the ability to really measure the full suite of alkyl nitrates that form. We started having measurements of total alkyl nitrates from groups like Ron Cohen's group at UC Berkeley, and now others measuring this in a total sense, often measuring significant fractions, say 10, 15% of the available reactive nitrogen being stored in alkyl nitrates. And to understand the chemistry, though, we would like to have that speciated in a molecular sense. And like I said, it can get pretty complicated once you start thinking about the actual pathways that a peroxy radical formed from isoprene can undertake. And so having some sort of constraint on these pathways, which are the most important, which nitrates survive, which don't, is really crucial through the process of field observations. And so I'm going to show you some results that we obtained over 2 different field observations. One is the Cenex campaign that was focused on the southeastern United States. Again, this was put forth by the NOAA group using the NOAA P3, and there were also simultaneous ground-based campaigns such as SOAS going on at the same time in Centerville here. And then also the high-scale campaign, which was the DOE funded campaign that used the DOE aircraft, the G1. And it was focused much more so in the region of Oklahoma that had biogenics as well as relatively low biogenic regions. targeting the interactions of aerosols and clouds in the sources of those aerosols through both anthropogenic and biogenic pathways. So in both of these cases, we deployed the time of flight chemical ionization mass spectrometer, and we were using primarily iodide ionization, iodide adduct formation, I should say. And this, of course, is through chemical ionization, inherently quantitative in that ultimately the formation of ions is controlled by the collisions between gases, gas phase ions, which we inherently understand through the kinetic theory of gases. And we used also on high scale, we switched back and forth between iodide adduct formation as well as essentially benzene cations. And these, we used their formation of clusters to measure a suite of precursors like isoprene itself and monoterpenes and some other species as well. I won't talk too much about this ionization process. And we've used others, not in the field, but also in the laboratory that I'll come back to at the end of the talk. But ultimately, this adduct formation is the pathway that we like to use. It does create some challenges in calibration because the formation of adducts is actually fairly selective in terms of the ability for the adduct to make a strong enough interaction to make it through the mass spectrometer. So it makes it selective, but also the calibration varies from molecule to molecule. But that's why we tend to start using different ligands and different reagent ions to allow us to access different classes of molecules. So we deploy this on both aircraft. And as I said, in one case, we were switching back and forth. In the other case, we were only measuring with the iodide adducts. And it was the first deployment, I should say, of the TOF SIMS on an aircraft. And this is work that Ben Lee has been looking at now for some time. And I say that not because he's slow, but because we have wanted to be extremely careful in what we put out in terms of the results, not only because of some of these calibration uncertainties, but because what we're finding is that there is essentially one organic nitrate that we measure that has this composition here, C4H7NO5, that is often the dominant, or at least the nitrate that we measure in the highest concentrations out of many dozens of different nitrates that stem from isoprene and monoterpenes in biogenic rich regions or anthropogenic VOC precursors when we're perturbed by anthropogenic pollution, aromatics from wildfires, and so on. But time and time again, and throughout the entire Cenex campaign over the Southeast United States, this one alkyl nitrate essentially made up more than a third of all of the organic nitrogen that we detected with this mass spectrometer. And so we wanted to understand, we asked the question, do we actually understand where this nitrate comes from? It's a bit complicated because it seems to be not a first generation process, but actually perhaps coming from many different pathways. And that would really then provide a test of whether we understand the processing of isoprene in a NOx-rich atmosphere if we could explain where this nitrate seems to come from in the atmosphere. And so just to give you some context, this is now looking only at the Cenex observations. These are looking at the sum of all of our alkyl nitrate measurements, or at least organic nitrate measurements that we measure with the iodide adduct ionization. What this figure is showing is that these organic nitrates that we detect are by and large secondary. They're not coming from direct emission processes because their contribution to the total reactive nitrogen reservoir is increasing with air mass photochemical age, as indicated by this 1 minus NOx over NOI. It's essentially a photochemical age axis. And then if we look at the distribution of, or the amount of these organic nitrates that we measure, the sum total relative to the total reactive nitrogen across different species, like the amount of an isoprene oxidation product that forms when NOx is low, or the concentrations of isoprene and monoterpenes and so on, what we find is that predominantly the highest fraction that organic nitrates make, that we detect, that make relative to the total reactive nitrogen are when the biogenic VOCs, isoprene and monoterpenes are the highest, and when you have NOx present or NOx available. So this is just telling us that what we measure by and large is driven by biogenic VOC interacting with NOx. And that isn't to say that we don't expect a nitrate to form from isoprene that has this composition. We would expect this to be coming from possibly common oxidation products like methacrylate or methylvinyl ketone that form from isoprene in high NOx environments. But the pathways to form this nitrate from those two are actually thought to be rather inefficient and perhaps not even form at all. So our goal is to really try to understand this. And if we go to the literature, such as the Caltech isoprene mechanism in the review paper published by Paul Wimberg and others, the work by Becky Schwantes and Calvin Bates that contributed to that review process and mechanism development. Essentially, there's, like I mentioned, multiple steps, but some involving daytime pathways and others involving what we might call nighttime pathways, in the sense that they're driven by the nitrate radical, or at least they form a species from the nitrate radical reacting with isoprene that then is processed at a different time of day, perhaps during the daytime. That gives rise to many different possible isomers. We only measure the molecular composition. We don't measure isomers. That's an important point to make. So we might be measuring the sum of different isomers that could come from different pathways. But our goal is to basically test these existing mechanisms in the literature. And I should also mention so Paul Shepson and his student from the SOAS campaign published a paper suggesting that this NO3 derived nitrate product of isoprene could be contributing to this nitrate that we're interested in, which they also found with the similar ionization chemistry to be the dominant nitrate that they measured. Okay, so what Ben has done then is basically use these literature values of different mechanisms to try and test whether we can explain the evolution of this one organic nitrate for the most part, although he has looked at the evolution of all of them simultaneously for the most part, but we're going to focus on this one for this talk. And so he's looking for experiments within the field data that he can do to constrain the model and test the model. So here he's used intercepts of two power plant plumes. Roger Sher power plant, I think, is one of these here. What they are don't really matter, but you can see downwind of these X's here. These are showing total reactive nitrogen measured on the aircraft going downwind from the source of a large nitrogen oxide source, the power plants. And in this time series, here you can see species such as this organic nitrate that we measure. And the green corresponds to when we were crossing this one power plant plume here. You can see that this nitrate's enhanced in those power plant plumes. Another nitrate is also enhanced in those plumes, but to a lesser degree. This would be consistent with the first generation isoprene hydroxynitrate. And then we also see enhancements in N2O5 that we measure with our iodide sims that are correlated in time with the enhancements of these nitrates within this power plant plume. And I should say this is during the daytime. We were making these measurements during this particular flight. So then what was interesting is the structure of this plume was such that the relative enhancement of this isoprene derived alkyl nitrate, we're pretty sure it's isoprene derived now, but given the correlation with other isoprene nitrates in the same plume, its structure was rather different than a lot of them. It was essentially one-sided on the plume, or it had a much greater enhancement on one side of the plume than the other, even though the photochemical age that we estimate across the plume was the same. And what was actually the only thing that was correlating is that NO3 related chemistry, including N2O5, as well as another nitrate that we are pretty sure only comes from NO3 adding to isoprene, were enhanced on that side of the plume, but not the other. So this gave us a pretty important clue that a major source of this C4H7NO5 that we measure across the Southeast United States is coming actually from NO3 related chemistry. And so to further address that, Ben constructed a model that he ran along photochemical age in those plumes and other plumes like urban plumes as well, using again the literature estimates for the different branching of different pathways to form this nitrate from isoprene. And the purple here is the only line you really need to see. The observed values of this, the importance of this C4 nitrate that I've been talking about, is shown in these black circles. These are what we measure as a function of distance downwind from a NOx source. And in order to explain that, basically half or more of the formation is coming from this NO3-derived pathway. The pathway is calculated based on the literature values from the Paul Shepson's work, but the yields of this NO3-derived product comes from the Wimberg Caltech isoprene mechanism. So we're actually having to merge two different mechanisms in order to simulate the abundance or even get close to it. We don't even get the full abundance using this NO3-derived isoprene oxidation pathway, daytime oxidation of an NO3 product. So the product could have been there regionally, of course, from nighttime processing of isoprene-rich air, make some of the precursors, and then the sun comes up. This then leads to third generation formation of this nitrate. But the point being that we think there's also earlier generation of this nitrate from daytime chemistry with NO3 going on in these NOx-rich plumes. That is daytime NO3 chemistry as well as daytime oxidation of NO3 products formed during the night. Yeah, so to summarize that, this alkyl nitrate C4H7NO5, it's the most abundant alkyl nitrate we measure across the eastern and southeastern United States. It's about 40% of all of the alkyl nitrates that we detect with the iodide TOF SIMS. Almost always, there's very few times where it is not the most abundant in that data set. It could be coming from a number of different isomers, but we're quite sure they're coming from isoprene in the end, and that the main pathway is actually significant production of this from NO3 plus isoprene-derived products, both the formation of those products during the daytime, but also their oxidation during the daytime, even though they were formed at night. And it's probably a relatively stable nitrate. There is going to be some photolysis and reaction with OH, but probably one of the main reasons why it builds up to be one of the dominant reservoirs is because it is less reactive than the other isoprene-derived nitrates, especially the first generation ones. So it's holding on to a substantial portion of NOx in the form of alkyl nitrates from isoprene. So we think this is a key alkyl nitrate to actually have in models and be able to describe in models, because if you can describe this pathway, you'll have a better chance of constraining where the other fraction of NOx may have gone, even though it went into alkyl nitrates from isoprene. Maybe it reacted to nitric acid in clouds and so on, but this would be an anchor for mechanisms, because we do think the chemistry is relatively accurate, although we have to simulate both NO3 as well as daytime OH oxidation. Yes, and so doing this analysis brought up the point, I'll just finish this here, that there very well is daytime NO3 chemistry going on, especially in NOx-rich power plant plumes. And the question is, does this happen elsewhere, such as in urban areas where we might also have NOx-rich plumes interacting with lots of isoprene? That's something for perhaps future campaigns to look into. Okay, so I'm going to move on to the next section, which again involves isoprene, but in a different environment, but still we'll be thinking about its interactions with NOx. And this is isoprene transport in chemistry in deep convection. As you can see, lots of evidence of deep convection in these anvil outflow from isolated thunderstorms over the Amazon and some larger scale systems. And I was interested in this most immediately motivated by the work of Andy Andrea, who showed there was lots of ultrafine particles in the upper troposphere over the Amazon, as indicated here by this figure showing the number of CN, which is usually dominated by the smallest particles, most enhanced in the region between 8 and 12 kilometers, which is right where you have most of these convective systems detraining in this region. So there's this connection between convection of material from the surface region of a biogenically enhanced region like the Amazon up to higher altitudes, and then new particle formation and growth. At least that's the idea, given the size of these particles are likely indicating relatively fresh formation and then growth in the outflow of these convective systems. And this connects well to lots of other literature on this topic. Of course, most recently, really well documented by the ATOM mission out over the oceans. And then I want to point out, though, or maybe I'm compelled to point out based on my previous affiliations, UC Berkeley, but also my current one at UW, that this idea of deep convection leading to new particle formation in the outflow has been kicked around for some time. in different regions, including over the continental regions, which is where here Andy Andrea is showing over the Amazon. And in these regions like the Amazon, a major component of organic material that can condense and contribute to particle growth would be isoprene. Of course, monoterpenes as well, and I'll come back to that. But what they do measure with, again, an AMS is that the background aerosol at these higher altitudes in the troposphere is largely organic. And so we have to be thinking about what particles could be giving, what processes could be giving particles that have organic rich composition. It could be that these are fires that are being lofted, and that's where the background aerosol comes, and that these new particles are of a different composition. But I think there is now enough evidence that we should really be concerned with the formation of new particles and condensation by low volatility organics, and especially in this region where the temperature is so low. It does not take particularly special organics to condense particles. So what we started doing when I was on sabbatical at Stockholm University, I started working with Roman Bartikov, a graduate student there. And we're using a cloud resolving model. So this is basically a high resolution meteorological model that operates on scales of 100-meter resolution in the vertical and a few 100-meter resolution in the horizontal. And we simulate a 200 by 200 kilometer domain. So we can basically resolve a medium-sized convective system. And we're not resolving all of the small steadies, but we're nonetheless resolving most of the material moving upwards and in downdrafts on the other side and so on. So what we did was take this cloud resolving model. It's also called an LES model. You might see it called that in the literature, Mimica. This was a collaboration by Stockholm University and MIT, I believe. And in this, we basically constrained a convective event that was based on thermodynamic profiles taken from the area around Manaus. So this is related essentially using Go Amazon field campaign data from a DOE project that took place there about 5 or 6 years ago, and then allowed this convective system to develop. And the cloud microphysics are included in the cloud resolving model. It's relatively simple cloud microphysics. There's 4 types of hydrometeors, basically liquid droplets and ice, 2 different forms, those that are precipitating and those that are still traveling with the updrafts and downdrafts. So then when that LES model is running, about 400 parcels are released at the base of the model, and then they are allowed to travel throughout the model domain following the convective flow, and those are output and saved. And so we have where each packet is in latitude, longitude, and altitude on time scale of about a second. And then we take those trajectories and we then use a parcel model, which has more detailed chemistry and microphysics, and specifically gas droplet, gas ice interactions, as well as gas-phase chemistry. And we run this model, this parcel model along each parcel and build up a statistics of what was going on chemically inside of these thunderstorms. So this was described in a previous paper, that the actual framework, and then the role of isoprene transporting chemistry was just published in Talis in 2021. And for that, I came up with a simplified isoprene mechanism, just so that the chemistry wouldn't take too long to solve. And it's based on a paper I published showing that we could capture with this mechanism the formation of secondary organic aerosol under at least low-ish NOx regimes. And our question here was, to what extent are isoprene oxidation products in the boundary layer and also formed aloft, to what extent are they going to be able to contribute to new particle formation? Because transport through the cloud will certainly scavenge a lot of those. How much chemistry is going on in the cloud itself, removing isoprene before it can get to the outflow region, and so on. So what is the chemical environment in terms of isoprene in the outflow region? And I should say we built a lot of this off of understanding that Mary Barth already basically described. But we did this on a slightly different scale and thought about the isoprene chemistry in detail. Okay, so what I don't want to, I'm not going to spend too much time on this, but what's was really important in our mind was illustrating how sensitive the distribution of oxidation products and the lifetime of isoprene in the outflow region, how dependent those were on whether or not we instituted lightning knocks. So a formation of nitrogen oxides by lightning flashes, of which over many regions of the Amazon, you will have a fair amount of lightning knocks produced. And in fact, in order for us to explain the vertical profile of knocks over the Amazon from the German Halo group and others, which were measuring up to 3 ppb knocks at 12 kilometers, we had to invoke a lot of lightning knocks being produced in the convective system, even though if we constrained it, constrained the lower atmosphere knocks, there was not enough transport of knocks from the surface to the outflow. So this was, in our minds, therefore, lightning generated knocks. And you could end up having a few ppb of knocks in the outflow of these clouds. And that is a huge perturbation to the oxidant field, but it's also a huge perturbation to the pathways that isoprene react under. And I don't know that that connection is really being understood in a lot of papers where we're thinking about what types of organics will make organic aerosol or new particle formation, that we have to be thinking about a highly NOx perturbed system, not just low NOx systems, when we're thinking about chemistry of organics in the outflow of deep convection. There was one other major lever on whether or not you would make low enough volatility organics to condense on existing aerosol, like isoprene growing aerosol, or we haven't looked at this, but we will be new particle formation, not necessarily by isoprene, but also the monoterpenes. This one big lever is actually whether or not in the anvil, where there's a lot of ice surface area, whether or not the organics that you form, the ones that are low volatility, do they condense to the ice? And that's a choice we have to make. Also, do the radicals condense to ice? All of these things were sensitive to whether or not we instituted gas phase transfer of these materials to the ice, as they would partition to either a cloud droplet or an organic aerosol. And if the answer is they partition about the same as they would to an organic aerosol, it's really hard to make any low volatility material until all the anvil ice is gone, because it just sucks up all of the organics. And so this will help us constrain whether and where new particles might have formed, and also where the growth is taking place. That being said, there does seem to be observations of fine particles right in the vicinity of some of the anvil outflows. So probably more work needs to be done on this. And so what we're going to be doing is adding in monoterpenes and isoprene and having them coupled together, because the RO2 interactions will be interesting, as well as the potential to nucleate and grow new particles. And we will be describing those mechanisms explicitly in these cloud resolved modeling schemes. Okay, so now I'm going to come to monoterpene chemistry. And as I indicated when we showed the classic view of biogenic VOC oxidation, we had a BVOC oxidant making RO2, and those RO2 could react a few different ways and react with NO, hydroproxy radical. They could react with other RO2 and so on. But this now we know from the past 10 years that this is missing a key process, which is that some fraction, especially in the case of monoterpenes and a few other VOCs, this has been recognized. There's a fraction of RO2 that are formed that undergo unimolecular reactions that are often internal H shifts. So the peroxy radical indicated here, the OO, grabs a hydrogen from somewhere else on the molecule, creating a transfer of the radical to the carbon, and then that allows for another oxygen to add. Okay. And then another one can take place if there's available hydrogens. So the peroxy radical formed here can then grab another hydrogen somewhere else on the molecule, make the peroxy radical side a different carbon, and make the hydroperoxide functional group, and so on. And what I will say is that this has really transformed how we think of aerosol formation and growth, this pathway in particular, especially from monoterpenes. So these create a class of compounds that are now called home for short, for highly oxygenated organic molecules. And they will have, in the case of monoterpenes, 10 carbons and 7 to 10 or even more oxygens. And if the RO2 that are formed by this, what we call odd oxidation pathway, end up cross-reacting, so through this pathway here of RO2 plus RO2, you can make what we call incorrectly dimers. They're accretion products, but they'll have 20 carbons, and then they'll have 12 to 18 oxygens. And so these are low to extremely low to supremely low volatility organics that can either nucleate and form new particles in the case of these home dimers, or contribute to the growth as in the home monomers. So yeah, that became apparent with this paper Mikhail N. wrote when I was on another sabbatical. So I keep saying that I need to keep going on sabbatical because we find these discoveries. And then this molecular understanding of atmospheric particle formation, that the actual growth of clusters was being driven by these highly oxygenated monomers and dimers, was shown by Siggy Schobesberger around the same time, actually before this, this paper came out. The cluster growth was indicated by Siggy and others in the cloud campaign. And then some of the estimates of how this odd oxidation process takes place and the formation of low and extremely low organics was recently input into WRF and simulated over the Amazon, and they could produce large amounts of ultrafine particles in the upper troposphere using, again, this organic oxidation as a source of low volatility organics, and really a VBS scheme that involved this process of odd oxidation. So obviously potentially very important is what I would say from a lot of that work. And we recently, with actually a summer student, Ro Chang, came to visit my lab in 2019. And I decided, based on his skill set and interest, that he could code some of this into GS Chem, which is a 3D chemistry model. So we basically tried to update as simply as we could, but a monoterpene RO2 chemistry, including this odd oxidation process, as well as enhanced peroxy radical cross reactions and so on. And there's a lot of leeway based on the literature of how we actually implement this, because the kinetics are still not well nailed down, I would say, and I'll try to demonstrate that. But here you're seeing distributions predicted by the model of home monomers. And you can see that in places like the Southeast US in summertime, as well as the equatorial tropical regions all year long, you're predicting of order a microgram per cubic meter of what we would consider condensable organic mass. Okay. So that could be 10% of the organic aerosol mass, or it could be 100% of the organic aerosol mass in some regions. This is in the boundary layer of the Amazon. Okay, and also the boreal forest, you may have a microgram per cubic meter, and that's the total amount. Okay. So if we include also these dimers, and these are more related to new particle formation, but obviously they will condense on existing aerosol and make secondary organic aerosol. I'll just point out here that we can get upwards of another 3 micrograms per cubic meter, especially in the equatorial regions, if we use relatively modest, not the highest formation of accretion products that are in the literature. If we include these, we can actually simulate factors of 2 or 3 more than the total organic aerosol in many continental regions that are influenced by monoterpene emissions. So clearly there's an important role now for understanding just how efficient is this process of odd oxidation, but also what is the fate of these home molecules. So we're not so sure that the formation of dimers are as efficient as some papers are suggesting. And we're also, though, not sure how fast home are actually removed from the aerosol, as Alma Hodzik has indicated that organic aerosol does have a photochemical loss in the atmosphere quite clearly, and she and others. And so this balance between formation and loss is now clearly important to get right, just by putting in what we think are the formation kinetics of these molecules here. And so one area that was kind of a mystery, I might have time for this, I'll try to be quick, is just what fraction of RO2 can do this? Okay, so from monoterpene, we think of alpha-pinene ozonolysis as a canonical system. Home molecules were produced by this system. It could be measured, but the actual mechanism by which they were produced was a puzzle for several years. So Theo Curtin tried to calculate every possible RO2 radical that was formed from the consensus view of how alpha-pinene ozonolysis happened. And no matter what, you had this cyclobutyl ring in the middle, and that's what we call the home wrecker, or I call it the home wrecker, because there's no way that these H shifts are energetically feasible because there's too much ring strain. So whatever peroxy radical was forming home, we had no idea. Okay, and so I sent Theo a couple of emails, said, I think you should try simulate what happens if this process here is bypassed to a different ring opening product and so on. It took me 1.5 years to sort of follow up on all of this. I finally sent him this little napkin. This was back in 2019. So why don't you calculate this? And it turned out it'd be really hard to calculate this, but it was easy for me to say you should calculate this. But the idea was that the energy in the Kriege radical is sufficient enough to start breaking more bonds before the end peroxy radicals are formed, and that maybe this ring actually opens. Okay? And we'll see this ring opening coming to play a little bit later. So it's just a little switching of the bonding in this to have the radical end up on this carbon after the cyclobutyl ring has opened. Again, there's a lot of energy deposited into this ozonide, basically, when the ozone adds to the double bond. And maybe this is what was happening. That was what I said in an email. And so he told me that he'd already done a lot of this and that I wasn't reading his papers completely. And I sent a few more emails saying, well, I think maybe this one particular one you haven't calculated. So they did. And that was done by Siddharth. And we basically come up with now an energetically possible production of peroxy radicals from ozonolysis that are the first generation that can go on and do odd oxidation. And so it's actually quite a treatise in this paper of all the pathways that are open to a radical that ends up ring breaking here. But to actually prove this was quite challenging computational chemistry with relativistic theory having to be brought into play and everything else. So far harder than I had imagined. It was easy for me to write it down on a napkin. But actually, so it was really impressive work. I encourage you to read that if you're inclined by quantum mechanics. But so we think this ring opening is really crucial for forming particles. So now we understand, actually, we can explain 3 or 4 different properties of the home molecules that form based on this ring opening. So we're quite happy. It's at least scientifically satisfying that we think we now know where those peroxy radicals come from. Right, so if we go to OH oxidation, there's a little bit less studies of monoterpene plus OH in forming home. We know they do form home from some work by Thorsten Berndt early on, but the rates and the yields are still a bit in question because each time someone does it, they use a different ion chemistry in their mass spectrometer and they get a kind of a different distribution. And so we set out to try to nail down what pathway was important for forming home. And in particular, just like ozonolysis can lead to a ring opening, when OH adds to this double bond, you can also get a ring opening. And Thorsten Berndt originally proposed that this was the peroxy radical that goes on to make home molecules through odd oxidation pathways. But there's quite a bit of disagreement. So the theory that's out there suggests it's maybe a 15% yield from OH reaction to this pathway. Recent work by Liu Zhu suggests it could be quite a bit higher, maybe 50%, and depending on the monoterpene, if it's beta-pinene, it could be closer to 100% going through this pathway, just increasing the potential for the formation of home. And so we aim to get at this chemistry by trying to target this particular peroxy radical using isotopically labeled alpha-pinene in this case, and we also have studied, not isotopically labeled, but also studied beta-pinene and limonene in this system that I'll show you. So we were trying to find tricks to detect how, the branching of this sort of directly with our mass spectrometry. And I need to thank Regan Thompson, who's at Northwestern, who synthesized this deuterated alpha-pinene starting material for us. So we are using this, what do we call the fast flow reactor, with in situ chemical ionization, where the reaction mixture is flowing past our mass spectrometer and we shoot ions across the reaction mixture. So there's no subsampling or anything like that alters the reaction time, and we can push probing of the chemistry at very short times. So I think from about 0.3 to 0.4 seconds up to 4 seconds is where we've been working. This was started by Yue Zhao as a postdoc, and then Ben Lee has been doing a lot of this work that I'll show you next in the lab. It does the chemistry, the ionization chemistry at atmospheric pressure and room temperature. So we started with about 150 parts per trillion of HOX, and that's what we expose alpha pinene, beta pinene, and limonene to. And then we ended up cranking up the nitrogen oxide to provide some competitive reaction rate studies to understand the H shift or odd oxidation timescales. Okay, so here's the distribution peroxy radicals you find with no NOx around or very little NOx. There's probably some NOx around, but that's a side story. From alpha pinene and beta pinene at 1 second reaction time with 150 ppt of HOX. Okay, so about half of that maybe at most is OH. So within 1 second, we have formed peroxy radicals with 3 oxygens, 5 oxygens, and 7 oxygens. And in some cases, we can get hints of 9. Okay, so that already puts a constraint on how fast these odd oxidation steps are if we're going to get multiple steps in under a second. So if it were 0.1 per second time constant, you would be talking about a timescale for one conversion of about 1 second, right? But we're seeing at least 2 here, so that's suggesting faster than 1 per second turnover times. And that's, I'll explain why that's important, but it gives us an understanding of how efficiently these will happen in the atmosphere. You also notice that there's a different distribution of these peroxy radicals between alpha pinene and beta pinene, suggesting these two have different propensities to undergo odd oxidation. When we add NO, nitric oxide, we make peroxy nitrate, or sorry, alkyl nitrates through the reaction of peroxy radicals with NO. And just want to point out that the spectrum of RO2 that I showed you ends up producing a similar spectrum of alkyl nitrates. That is, we see alkyl nitrates forming from peroxy radicals with 3, 4, 5, 6, 7, and 8 oxygens on them. Okay, so that means the odd oxidation had to happen even when there is NO present. So it's competing with the NO that we're adding, that again, under 4 seconds. So this is telling us that the timescales for odd oxidation are quite fast. Okay, so now that means really, if it's really fast, it may not matter so much in the atmosphere what else is going on. It's what is the yield of the peroxy radicals that can actually do this transformation. And so that's what Ben has spent a lot of time on, and that's what we've been using this deuterated alpha pinene starting material, where we can add NO, and that should compete with odd oxidation. This is an example where this peroxy radical adds to a double bond, and that then creates a new radical center. But if we add NO to compete with this, we'll make an alkoxy radical, and that alkoxy radical should spit off deuterated acetone. And so we should be able to just measure deuterated acetone as a function of NO, and relative to the amount of alpha pinene that's reacted, we'll get essentially a simple relationship, which is a factor times X over a constant plus X. So it would have some shape like this as a function of NO, where the ultimate plateau region is telling us about the fraction of peroxy radicals like this that are formed, which is the yield of the peroxy radicals that can actually do the odd oxidation. And then this period, the point where this curve turns over, is telling us about the competition between odd oxidation and the reaction with NO. And so that's what these look like: the deuterated acetone from alpha pinene, regular acetone from beta pinene. You can see actually they share relatively similar initial slope, but then the alpha pinene seems to be turning over faster than the beta pinene acetone. And what you'll notice is that we don't get to these turning over essentially at all. We don't get a flat line for several NO, which means we haven't really suppressed completely odd oxidation, and we haven't even come close to suppressing odd oxidation in beta pinene. We've gotten close with alpha pinene. Let's see. Looks like my laser pointer or my mouse has died, one or the other. Okay, so this is important because it tells us the first odd oxidation step at the very least is really fast. In order to compete with the amount of NO that we are adding. The axis here is in ppb, and we're at 40, 60, 80 ppb in this flow tube. It's not a lot of time, So you do need a lot of NO to do the competition, but we're talking about odd oxidation pathways happening at 7 to 10 per second, okay, and a yield at 20% from alpha pinene. And so that's what's summarized on this figure, giving you a sense of how fast these peroxy radicals will transform themselves into having 7 oxygen atoms. So 10 per second and 7 per second are the 2 steps that, of odd oxidation that we've constrained. I want to point out that in this modeling study, we used at most an odd oxidation time constant of 1 per second, not 10 per second, as indicated by the flow tube results. And we consider this the upper limit in our model. Okay, so we also have a whole simulation that we talk about where we have a slow odd oxidation rate, which is 0.1 per second. So basically this, before we've even gotten this submitted, is probably out of date, but it'll still be useful for showing where the competition happens. And what I'm showing in this figure here is, we're going to just look at this scenario, the fraction of these peroxy radicals that are formed that can undergo oxidation, the fraction of them that react with NO. The fraction that do odd oxidation in competition with NO. So where this map is basically orange, it's 100% of them undergo odd oxidation at 1 per second, at 2 by 2.5 degrees resolution in the model. So there are probably some high NOx hotspots where this is competitive, where NOx is competitive, but for the most part, these are just going to form even in polluted regions. So there's some notion that maybe odd oxidation is outcompeted in urban areas, at least not for monoterpenes. That's what I'd argue. Yes, so I'm almost done here, finishing up. For beta pinene, it's just as efficient, if not more so, the first step. And there's some differences that vary between these different structures of alpha pinene, beta pinene, and limonene. But nonetheless, in alpha pinene, we have about 20% undergoing odd oxidation at about 5 to 10 per second rates. Beta pinene, we have maybe 65% undergoing odd oxidation, initially at 35 per second. And then they get to this O5 molecule that seems, where the odd oxidation seems to slow down quite a bit. And gets back to more normal levels between 1 and 5 per second. Okay. So this, these are really fast. That's what I think the key point. And beta pinene is a potential, should be, for efficient, low to extremely low volatility organic vapor formation. Although maybe there's not as much beta pinene globally in a global average sense, but it really suggests we need to understand that better. So monoterpenes plus OH will efficiently make home and therefore contribute to aerosol as well as home nitrates, even at high NOx. But the distribution of RO2 is basically there, even if the NO is 3 ppb, okay, because 3 ppb is about 1 per second. The 3 ppb NO is not even going to compete with the first couple of steps. And so that means home formation will be efficient, and we need to understand home losses much more than we do. And I won't get into that, but there are some studies out there now that are showing that home losses may be substantial, photochemical losses. Okay, with that, I'm going to end and just summarize here. So we have, from the first part of the talk, we have a single C4 nitrate that we measure across the southeastern United States. It's a major contribution to the sum total of organic nitrates that we measure in the Cenex campaign, if not the dominant one. And it seems to be, its formation seems to have a significant role for NO3-driven chemistry. These are coming out probably in 2 papers, maybe not companion papers, but there's work that I've been involved with Nondas Tsiligiannis, who's at Gothenburg University, and then Ben Lee is doing the Cenex work. And we did some chamber experiments with the Ulish chamber group, and Julie Fry and Steve Brown were involved in this. So that also formed a lot of what Ben and I were thinking about with the Cenex analyses. Then when we start thinking about isoprene oxidation in other regions like upper troposphere, in the outflow of thunderstorms, it could be very fast if there's lightning NOx that can sustain the cycling of OH. And so lightning NOx will play a crucial role in setting the growth environment, so the distribution of products. A lot of these will be nitrates, low volatility products, so essentially nitrate chemistry or I should say alkyl nitrate chemistry being important for some of the products that might condense. That was work I did with Stockholm University and Roman Borodnikov. And then finally, these laboratory kinetics that Ben Lee has been working on are showing that monoterpene oxidation is a massive potential source of SOA through the formation of home, even at high NOx. But we really need further constraints. And I would like to point out some of those constraints coming from Siddharth Iyer's theoretical work, as I mentioned, from ozonolysis, and then Rochong Zhu's work with Chem and Ben Lee's laboratory kinetics. And I'll stop there and take any questions.
Thanks, Joel, for your talk. Super interesting. We have already a couple of questions. This one is about calibrations, apparently.
Oh, yes.
Joel, yeah. Great talk. I'm just wondering how much of these results, C4 nitrate, could change with sensitivity changes for this formula. What sensitivity was used in this work, as the figure are reported in PPT? And is it expected to change? And how is the calibration done?
Yes, great question, very insightful, obviously. So let's see if I can, so the results are somewhat dependent on sensitivity, of course. So we used the calibration we did to an isoprene hydroxynitrate that was synthesized for us from by collaborators at UC Berkeley and Caltech. And we use that calibration, we use the most sensitive one we determined. So if it is unlikely to be more than a factor of 2 more sensitive, and we're still, this is going to be higher than most nitrates that we measured than a factor of 2. So even if we use the highest sensitivity possible, it's still going to be a major, if not dominant, organic nitrate. If anything, based on the structure that we think it has, we might expect it to be a little bit less sensitive, so there could even be more of it. I mean, that's where we're standing. So we kind of are using a middle of the road value, but there isn't anything that suggests it should be the most sensitive, detection we have. So it's definitely uncertain, but I think we're using a pretty conservative value for the calibration. Yeah. But
very good.
That will be detailed in the paper, I promise.
Okay. Another question. Does monoterpene autooxidation compete with RO2 plus HO2 reaction as well?
Yes. And so I didn't show any of these, but we have products, we have measurements of what we call the closed shell products that would form from RO2 plus HO2, where you would transfer the hydrogen and make a hydroperoxide moiety. It's a little bit hard to tell if that's what's really going on in our experiments. We have certainly measured what's consistent with that process. And in the flow tube, I didn't show this. I could show this. Maybe I can go back and show that, where we have tried to constrain how much HO2 is in the flow reactor, because our Hawk source does make OH, and it also makes HO2. So we have HO2 coming out of our Hawk source. So I'm just going to share my screen here and try to find a slide here. Okay, yeah, so what we did was, instead of the monoterpene that we exposed to our Hawk source, we put in isopropanol, and isopropanol will make acetone after it reacts with OH. And then as we add NO, we'll make more OH, because the HO2 will react with the NO to make OH. So it's a little bit complicated when we start adding NO, that actually quite a bit of different pathways take off. And Ben has been doing quite a bit of simulations of this flow tube situation when we add NO. It gets very complicated because alkoxy radical chemistry starts taking off. And so we're trying to explain quite a bit. Anyways, the point here is that we have a model and the observed acetone. The acetone is calibrated independently in the system. And so we are quite confident that at least the initial Hawk's distribution that we exposed the monoterpenes to is about 125 ppt HO2. So even at that level, which is higher than the atmosphere typically, the autooxidation takes off. Yeah.
Okay, we have a couple of more questions. Lots of great work. Your work showing that NO3 chemistry is important in the daytime in Southwest power plant plumes is very nice and interesting. The production rate must be pretty high. Have you speculated where else this chemistry is likely to be important? I think you mentioned it.
Well, so I mentioned I speculated it. Where else might it be important was the question that I think would be interesting to ask, given that we do have some evidence that it's happening in these power plant plumes. But in the power plant plumes, NOx is quite high. So summertime ozone, you have 10 ppb of NO2. So NO2 plus ozone is quite high. And so that's making the NO3 radical. I assume that's what they mean by the production rate of NO3 must be high. But yes, it is high. And so it's going to scale with NO2 times ozone. So wherever that is high, we should be thinking about this daytime NO3 chemistry. The issue is that, and other people have pointed this out, Julie Fry has a paper on daytime NO3 chemistry, maybe at the SOAS site, I forget exactly where, but you don't need a lot of NO3 to compete with OH, or it seems like you would, but there's, if you have 10 ppb of NOx, a small fraction, like less than 1 ppt of it being NO3, doesn't take much to start perturbing pathways to be competitive with like OH and ozonolysis. So yeah, I do think we should be on the lookout for this in different ways, and we think we will identify in this paper what nitrates we think are good markers of NO3 derived nitrates from isoprene. And others have shown some of this as well in the Wenberg group.
Okay, one more question from Jeff. Great talk. The nitrate from OH oxidation of the isoprene products is obviously isometric with an alcohol from nitrate addition. Any way to do fancy fragmentation to find out which was dominant, assuming external addition?
Yeah, I mean, in the laboratory, we could probably come up with a way to do that. And I should point out, I think, let me see, maybe I should check that I understand exactly which he's looking at here. Oh, here's the share screen. I can quickly go back to this. It was very cartoonish. So I don't think it'll take me that long to get back there, but I think he might be talking about this slide. Maybe he can comment, but so there's a few different pathways to get, for example, from here with NO3 addition. It doesn't necessarily involve NO3 addition or here maybe, or here. And I think we can't tell the difference from the field data if it's this one or this one. We did try to do some laboratory studies with Nondas, who I was mentioning was a student from Gothenburg University in our lab. And we didn't get that working well enough to really prove which pathway was most important to get to this C4705. In the Eulish chamber, there's a bit more information, but again, we didn't do any sort of fancy labeling or targeting of certain groups. So, but I think it would be really great to do that now that and that would help us figure out which of these are we talking about here. Yeah, so if he has ideas, I'm open to hearing them. Yeah.
Sounds good. Well, thank you again for the great talk and your time answering questions. And thank you everybody for tuning in. See you next time.
Thank you. Bye-bye.